All right, welcome back, everybody. So in this session, we have two different talks. We're going to go a little bit more in depth and then have time set aside for questions. So my name is Kevin Clarno. I am an associate professor here in the Nuclear Reactor Engineering program, as well as the Odin Institute for Computational Engineering and Sciences. I'm going to talk about a project that we've been working on associated with digital twins for advanced nuclear reactors. And then Dr. Haas will come up next. He's going to be talking about a project that we've been working on associated with building a advanced nuclear reactor in Abilene. So at a high level, one of the things that you might have picked up on from some of the earlier talks is, in general, nuclear energy doesn't rapidly innovate. This concept that you see in so many other fields of you have a new iPhone that comes out every 18 months and people are waiting in line to get that next one. There is rapid innovation in some fields, and it just doesn't really happen in nuclear. Changes tend to be very evolutionary in nature. Slight modifications to an existing, known, comforted system. In a lot of ways, there have been many major changes proposed to the traditional nuclear reactors that never made it to market. Mixed oxide fuel that had uranium and plutonium together, accident-tolerant fuels, and high burn-up claddings. The time from Fukushima all the way to now, we can see that we've had 14 years, and yet we don't have widespread use of these accident-tolerant fuels or cladding. And a lot of that is really driven by what does it take in order to get the idea, evaluate, experiment how to make that idea work, and then get it through that licensing process. And so current trends that we see in energy usage suggest that by 2040, we're going to be building tens of reactors per year in the US alone. Worldwide, it's going to be even more significant. And so if we're building that many reactors, we can't follow the same process that we have followed historically. Because the reality is viable economics won't persist if we can't innovate. So something fundamentally has to change. So we got funding from the state of Texas in the last budget cycle that is really looking at what can we do in order to use the computing power available to us to integrate simulation and our operating systems to understand how we can innovate faster and get those innovations licensed through the nuclear regulators. The focus, one of the pieces of this was on molten salt reactors. In the US, or in Texas, there are two different types of molten salt reactors that have been considered on the Rellis campus. There is, at Texas A&M, they're considering building both a molten salt reactor, which has liquid fuel and uses high temperature liquid salt, and a liquid salt cooled reactor with the solid fuel, TRISO fuel that Dr. Subi was talking about earlier. Molten salt is a effective high temperature heat transfer medium that is being used in reactors. And so we wanted to look at, starting with a focus on these molten salt reactors, what can we do to understand this process and how we can improve it from a licensing standpoint. So the first piece, in nuclear reactors, traditionally instrumentation is used to understand the safety of the reactor. I want to know if there is some critical limit, that I want to make sure that I don't exceed some critical safety limit. And so we need to start to change the understanding of instrumentation in our systems from just safety-centric to really knowledge generation. What is happening everywhere in my system? How do I know it's happening? How do I understand what's happening throughout the system? And we have to have software that begins to add value to the facility immediately. In all of these advanced reactor projects, we see that research is something that is constantly put off. It's something that is going to happen in the future. We need to get the first reactor built. We need to get it licensed, constructed. There is this huge giant hurdle in nuclear, which is this first-of-a-kind reactor. And the concept that once we build this first-of-a-kind reactor, we'll be able to do all kinds of things after that. You could create, with machine learning today, you could gather all the operational data from some physical system, feed it into your machine learned neural network, have some real-time analysis of that data to provide some automated controls and make that system operate better. But that just simple machine learning structure would be a digital twin, a computational twin of that physical system, but it doesn't have physics. It doesn't have knowledge of the science behind this system. And so because of that, it really can't effectively predict beyond what experience you have. So the other element that would need to come into this is you need to incorporate physics that is more comprehensive and more first principles. Your physics has to incorporate the things that are happening inside of the system, the dynamics of the system, the chemistry, the nuclear radiation transport, the heat transfer. All of these things need to be incorporated, and you have to incorporate the full facility. You can't just look component by component. And one of the things that we understand is with the advanced data gathering that we have, we can improve our software with time. And so in many ways, historically with the regulator, you will create a piece of software that says this software is modeling this nuclear system. And you go to the regulator and you say, let me show you all the evidence that shows that my software accurately predicts this system today. And now I'm stuck with that software, because I went through a very expensive licensing process, and changing that software is something that becomes burdensome because you have to go back to the regulator and say, I know I changed it. I said it was great before. I've changed it and made it much better, so let me take that modification and incorporate it. And so that the regulation on advancing and changing and improving your software becomes very burdensome. But we can't be stuck with fixed software, especially with these advanced reactors, because we're learning constantly as we have non-nuclear and nuclear testing facilities. We're learning more and more about these systems. So we need that software to be able to improve with time. And so you can envision some type of structure that would look like this, where you have your physical system and you're passing that operational data to some sensitivity uncertainty analysis tool that would be used to calibrate, do inference modeling to improve the high fidelity physics codes that have all the physics built into it. And then you use those high fidelity physics codes to create and improve the accuracy on some physics-based engineering codes. And now with that system, that physics-based engineering code could be used for some operational guidance and some automated controls. It can gather real-time data straight from that physical system. And so you have almost a loop-based structure. One of the other struggles in nuclear is cybersecurity. Cybersecurity is not something that can be ignored. If you have some operating physical system that's being controlled or operators are being informed by some physics-based code, you need to make sure that nobody can break into that. And so you need some fundamental physical controls. And so that piece, that bottom right triangle, can be sitting there locally on site. And all of the things done in the top left side can be done with some remote supercomputer. And that way you have established cybersecurity firewalls and protections to make sure that it is protected and guarded. And so now you can imagine you have this new system where you have new instrumentation. You have software that's trying to improve the operation of the facility. That software has all of the physics so that as you gather more data, you can improve the software with time. And you're really building in more of this capability. But all of this is a whole lot of pieces, a whole lot of different work, a whole lot of components. And so if you're just doing this for one single facility, it really isn't going to gain much value. It's going to cost way more than it would ever provide. But when we imagine a time where we have a company or a suite of companies that have many different physical systems. They may be operating nuclear reactors, they may be university research reactors, they may be non-nuclear flow loops and test facilities. You have a whole bunch of different physical systems that are all instrumented well, are all providing instrumentation into one sort of data acquisition database that can provide all of that and do the sensitivity, uncertainty, the calibration pieces to improve that one high-fidelity physics code suite. And you use that high-fidelity physics code suite to create physics-based engineering codes that actually provide on-site, real-time models that can help those systems operate locally. Now you can do cybersecurity in an integrated way. You can look at each one of these pieces and make sure they are all cyber protected. They can each have their own digital twin that is associated with their own physical system, but they are all based on a single high-fidelity code base. By having calibration from many different physical systems, you can have things like your operating commercial reactor that is not going to change, that is not going to operate differently. You want it to be up and running, and nobody messes with it. Nobody does anything unique. But you can also have your experimental reactor or your non-nuclear test facility that you can change them, you can adjust them, you can put in new pieces, you can put in new instrumentation, and gain and add more data. And so with this sort of environment or infrastructure, you can imagine a time when we have more and more physical systems just keep getting added on and added on to your infrastructure. And as you want to evaluate a new system, you could say, let me build in a new non-nuclear test flow loop and gain more data on my new pump or my new heat exchanger, and add that information to that full data acquisition system so that it's incorporated and we can begin to understand how that accuracy changes with time and with operation. So at a high level, this is what we are hoping to sort of demonstrate this concept in practice. In reality, the nuclear industry isn't looking there, and the Nuclear Regulatory Commission is not ready for something like this at all. And so this is something that we need to be able to communicate the idea behind this, what it would really look like to the regulator, to the industry, to investors, and fundamentally begin to build and understand what this technology looks like in practice, because it's easy to show a PowerPoint and say this is what it looks like on a PowerPoint slide, but what does this really mean? And so we have several different of these physical systems that we're trying to create digital twins of. I'm going to go into a little bit more depth on one of them in particular, but we have partnerships with an experimental system at MIT, at our own nuclear reactor at UT, and another experiment system at Texas A&M, and we have other partners that we're looking to work with to understand how would you do this, what would it look like, where is that value gained. And so for the UT nuclear reactor, for those who aren't aware, there is a nuclear reactor on the J.J. Pickle campus. It is a TRIGA-style nuclear reactor. These reactors are extremely safe. It is very difficult to even imagine a way that there could be an accident that could harm the public. One of the standard experiments they do is taking a neutron-absorbing control rod and pneumatically ejecting it from the core just to watch the power go from 50 watts all the way up to 1.21 gigawatts. And I just like saying 1.21 gigawatts. And so this reactor turns on and off every single day. It's an 8-hour-a-day operational cycle. Most commercial reactors, they turn on, they go full power, and they operate 18 or 24 months without shutting down. And so the operating cycle, the things that are done with this research reactor, add a whole lot more uniqueness and variety to the data that is gained. We also have a lot more control with this reactor where we can say, let's add some new instrumentation. Let's understand what would happen when we change out instrumentation. So we have a lot of control over what we do with this reactor. And so we are going to try to demonstrate this process for this reactor, and then anytime we change the system, whether it is putting in new fuel and shuffling where the fuel is, we are changing the dynamics of this. And our hope and expectation is our high fidelity code stays accurate even when you change that system. And that way we can demonstrate to the end users that as the system changes, as it evolves, the software remains accurate, remains predictive of what would happen in the future. And as you put the reactor in all kinds of crazy operational states, like, hey, let's see if we eject the control rod, it can accurately predict both the long-term evolution of the reactor as well as the short-term variant systems. So we have a high-fidelity 3D multiphysics tool that is modeling that reactor. That tool has been used to create a real-time model that can predict the full 3D power distribution, and we are looking at using it to guide that operation of the reactor itself. And then we're starting to build in automation of this process as a whole. And so the data acquisition from the reactor, that data from the control room is gathered on, I believe it's a 10 hertz scale, and sent to our supercomputer, the Texas Advanced Computing Center supercomputer nightly. That data is being analyzed to look for trends in it and characterize the operational state of the reactor to support the simulation piece. And then we have what is called a digital shadow. And so while the reactor operates from 8 to 5 each day, at midnight all that operational data is sent to TAC, and we have the high fidelity code models what happened the previous day. And so for a few hours each night, it sets up the model and it gathers all that operational data, and it says, here's how the reactors operated it, here's what the instrumentation measured, here's how my computer code modeled that same instrumentation, that same system, and here's what the computer code predicted for what the instrumentation should have said. Let's evaluate what is the difference. Let's understand where the errors are, at what states is it problematic that we need to improve the accuracy, and quantify how accurate that system is. And then it can also be used to project, this is what it should look like the next day when you start up that operation. So then we have that high fidelity code, and with it, we're predicting that next day's operation. We're providing the experimentalists with a whole lot more information than they've ever had before. Previously, they had information based on that instrumentation. Here are some locations where I'm measuring things. Now with this high fidelity physics code, we're able to tell them everything that is happening in their experiment everywhere throughout that system during the entire operation of that previous day. So they get dramatically more information. But we're also able to use that high fidelity code to create these real-time models. And so we can occasionally update the different real-time models for short and long-term transients. And as that high fidelity code improves, as you get more and more data to make that code more accurate, this real-time model should become more accurate. And we can use it to provide in real time the 3D power distribution, the margin to licensing and safety limits and things like that. And so in this ways, it can operate as a digital twin to the operation in real time. And if you have a digital twin that is operating in real time alongside your physical system, then you can start to look at what would it mean to provide some automated controls. And so we are building in an experiment where we're putting in a neutron absorbing rod inside of the nuclear reactor that can be controlled by this digital twin. And that experimental system, since it isn't associated with the licensing of the reactor, it is just an experiment, it can do fine-tuned power control of the reactor operation and demonstrate autonomous control of a nuclear reactor with a digital twin. And as we continue to operate the reactor during its standard, normal, whatever the reactor does, operational business, we're gathering more and more data to understand how can we improve the high fidelity code, how can we improve these real-time models, how can we improve the autonomous control, and how can we evaluate the cybersecurity of this entire infrastructure. So what you can see in this is not a one-person project. There are a lot of different pieces to this, a lot of overlapping pieces. And when you're doing things with students, you need to make sure that you're understanding, how do I carve out a piece so that a student can be individually successful and not dependent upon everything else. Otherwise, you wind up, when you have a circle of no students can ever graduate until they've all graduated. And so fundamentally, you have to break this down into separable chunks so that each individual, each team can be successful. But when you start to put it all together, you have this fully integrated, coordinated piece. So this is something that we're working on and think that it can have a big impact in the industry. Now I'm going to pass it over to Dr. Haas to talk about our molten salt reactor design and licensing project, where hopefully we get a reactor that has a bunch of cool instrumentation that we can use to generate a bunch of data for something like this. And we'll take questions for both of these after that. Yeah.
Let's see, there we go. I had a feeling when we developed the agenda that if we got Dr. Clarno up here talking about digital twins, I might not have a full 15 minutes to talk about this. I'll keep it fairly quick. In 2020, a group came to UT and asked if we would be interested in joining a team to try to build a new reactor in Abilene. I thought it was fairly crazy. I was planning my trip up there to go find out about it, and my wife said, "Why are you going to Abilene to do nuclear stuff?" And I said, "Well, there's folks out there that have got an idea, and we have to try to get involved. If this is going to happen, we want to be involved in it." This crazy idea had legs and support from an oil and gas man that really wanted to push it forward. So starting in 2020, we had a blank whiteboard and an idea to build a nuclear reactor. We filled out that whiteboard and then kept going until we submitted a construction permit to the Nuclear Regulatory Commission in 2022 to try to build this reactor. It was going to be a 1 megawatt research reactor, basically very similar to the one we have on the research campus here in Austin. And it won't produce any electricity. It will not even have locations for us to irradiate lots of samples like we do with our reactor. But what it will do is be a test reactor that gets us the data that we need to go take to a licensing body like the Nuclear Regulatory Commission to develop that. So Natura Resources was the company that was founded to fund this. We were part of a consortium with Abilene Christian University, who's hosting the reactor and owning the reactor, Texas A&M University, and Georgia Tech. So we all got together, multi-university project. If anybody's been a part of these multi-institutional projects, you can know that they might start off sounding great, but then things get complicated with rivalries and people wanting to own different scope. It's really been an amazing project to be a part of because we've been able to bring everybody together to push forward on this project, even if you might miss out on some little bit of scope that you thought you'd really like to work on, but in the interest of pushing forward, we're going to separate it out the way it makes most sense. We were invited to give a talk by the Energy Institute in 2022 in September, and we titled that talk, Building a Molten Salt Reactor in Texas by 2025. We're going to miss that deadline. So we said then it was incredibly aggressive, but the whole point of this project was to be so incredibly aggressive and push the boundaries. We said we're going to design a reactor that the NRC, the Nuclear Regulatory Commission, can't help but approve it. And so that's the entire thought process throughout the whole project. Everybody has stuck to that, and it's been a really amazing project to be a part of. We are now targeting late 2026 to early 2027 to turn that on. We're still considering that a pretty good success in the history of nuclear projects to be about 2 years late from a very aggressive project to start. So basically where we are now is we're continuing to work with our other university collaborators and with Natura Resources, as well as Zachry Engineering, who's taken on the role of the engineering partner on the project. We are submitting the final safety analysis report. So this is the last document that really goes to the NRC to allow us to put fuel in the reactor and turn it on. We are building the reactor itself. So we have the permit from the NRC to build the reactor. So that's in process of finalizing the design, sending it off for construction. The reactor is going to be built in a factory. It's going to be shipped to Abilene Christian and lowered into a trench in a building that already exists. So Abilene Christian University, with Natura's help, has the only advanced nuclear reactor facility ready to go in the country. So most other projects are basically building the reactor and building that it will sit in at the same time. Natura and ACU came up with an idea to take advantage of the way that some of the laws are written, that a research reactor can be put into an existing facility. And so there's actually a very similar project happening at Idaho National Lab where they're taking older facilities where smaller reactors have been run in the past. They're revitalizing those facilities and they're going to bring in commercial reactors, microreactors basically. But part of this is demonstrating the idea of building a reactor in a factory, shipping it to the site, emplacing it, and then getting the approval to turn that on. So that's my rapid rundown on the current status of the reactor. I think we'll open it up to questions. Obviously, we would definitely love for that reactor to feed data into a digital twin here at UT Austin. And we think it could be really valuable for that company, for Natura's projects going forward. We also think that it can help demonstrate digital twins to any other company that wants to do this. So last thing, little pitch, we have a panel on Thursday at 1:45 in the afternoon. On that panel will be the Vice President of Engineering for Natura Resources to talk about what they've been doing, and then we'll also have the French attaché to the United States for nuclear energy, Sunil Felix. The two of them will be talking, I'll be moderating, to talk about some of the challenges and how we can overcome those challenges in nuclear. So with that, I'll open it up for questions. Yes? Oh, and sorry, we have a microphone set up here now for questions for anybody, if you wouldn't mind. That way it gets it on the recording. Okay.
Who's building, so when it gets, who's building what's going to, when the reactor gets delivered here to Abilene? You said it's being manufactured off-site.
Right.
Who's doing it?
So I actually don't know who's doing the specific engineering. Zachry Engineering is doing the engineering side of it. They'll be working with contractors to actually build the components and then assemble them. One of the other companies that we're working for is Teledyne Brown, and there's that aspect of it. One of the interesting things about a liquid-fueled molten salt reactor is you operate at effectively atmospheric pressure. So you don't have to have this massive forged steel vessel that the reactor goes in. One of the limitations on high-pressure reactors is there are only a few forges in the world that can make these very large, very high-pressure reactor vessels. When you go to lower pressure, that opens it up to many, many more steel manufacturers where they could build these components. So I think that'll be contracted out for, it'll be put out for bid and then and contracted.
Do you still maintain that website that people can go and see how it's coming along?
So Natura Resources has a website where they're constantly adding updates for their news articles. There's some cool things showing the construction of the building, the time lapse to actually build that building. ACU has a website as well that they update, but I think Natura is probably the one that has the most up-to-date news articles and things like that. You bet.
But now that the building is complete, there's no need for a time lapse to show the building's change.
It's there, yeah. It's not changing much. Other questions? Yeah, if you don't mind.
So I'm quite interested in the fact that you can just manufacture something and plop it down in an existing facility. Is this a model that might be used? I mean, it sounds like you said you started in 2020. Does this take to just have an adjacent nuclear facility? Oh, sorry.
Yes. So under the current rules, the building that a commercial reactor goes in has to be part of the licensing process for any reactor. I don't see those being changed in the near future, but there are folks that are interested, let's say not for data centers, but NOV has a subsidiary called Shepherd Power, and they've engaged with the regulator to say, if we scale back the size of the reactors and minimize the risk and put those reactor designs through your regulatory process, can we change the siting paradigm so that we don't have to have everything geared towards gigawatt scale reactors going forward? So there is an effort underway to modify the regulations on that side. Right now, the way that you can do this is only if it's for a research reactor, is the way the current regulations allows that. So research reactor, there used to be a limit on power, that's actually been modified. But the main constraint on a research reactor is you're limited to the cost recovery that you can get for selling the product of that reactor. So if you're producing energy or you are producing isotopes, there's a limit on how much of your costs you can recover, and it makes sure that you're not profitable. If you become profitable, you have to go through the traditional regulatory framework. Yeah.
For those of us that remember MSRs, like from the 70s or whatever, they were like, the first one I ever saw was for a hospital.
Really?
So size-wise, what are kind of your general ideas, like Air Force Base or, whatever, size-wise on these? What do you think?
So the question was about what is the size, and I'm guessing power output is really what you're talking about. So interesting, physical size. The molten salt reactor at Abilene Christian University is going to be, the whole container is going to be about 15 feet diameter, and then 35 feet tall, 35 feet tall. And that's 1 megawatt thermal. To expand that, you don't get much bigger. Because of the way nuclear power works, it's certainly not a linear increase in volume. It's really more about how much energy can you take out of the core, how quickly can you get energy removed from the core. So you're not really limited by size. The main limitations on reactors going forward is how you intend to deploy them. So small modular reactors, the idea is to build them as much as possible in a factory, ship them to the site, and then do the final regulatory oversight of the installation of that. You have to make it go down the roads. So there's a width limitation around 18 feet for getting things down the road in Texas. It's less on the East Coast, and it's even less allowed in Europe. And so it depends kind of where you want to deploy. But I could see reactors sharing the roads with the wind turbine blades that are currently on our highways all the time. That's really one of the main limitations. I think that's going to drive reactors into the 250 megawatt thermal range. And so they will stay in that small modular reactor. There is definitely a push to get more economies of scale in terms of power output per reactor. And at some point, your drive to get more power output from the single reactor increases your safety requirements. So you have to have more active safety. So this is what Dr. Charlton was talking about earlier. The higher total power level of your reactor, the more active safety systems you need to cool down that reactor after you shut it down. And so one of the things about this kind of sweet spot in the few hundred megawatt thermal range is that you can maintain passive safety that's inherently safe without having to increase the cost. And we talk about safety a lot in the nuclear industry. What we're really talking about is we already have very, very safe reactors. It's one of the safest forms of energy we can produce. If you can make the reactors more inherently safe, you can drive down the cost. The cost is the problem with nuclear right now. It's not actually the safety. We have a PR problem when it comes to safety, but really the reason that more nuclear is not being adopted is because of the cost. And so if we can make the reactors more inherently safe and reduce the regulatory burden, then we can allow ourselves to innovate and bring the cost down rapidly. And so that's really what we mean when we say making the reactors safer. Yep.
Saying when it comes to the safety aspects, you don't have to worry about any of these hydrogen accumulation, that kind of stuff, and you just worry about, even if it's thermal, if it just melts and it just forms a pit there, it's essentially that.
Exactly. So with certain reactor designs, if you move away from water as your coolant, then you don't have the steam issue anymore where you can have, one, you have the high pressures of dealing with steam, and you put high pressure steam right next to radioactive materials, you need to layer on a lot of safety systems around that. If you have a different reactor coolant, like molten salt, that won't flash to a vapor until the steel around it melts into a puddle. And so you would absolutely have a mess to clean up, but you don't have the opportunity for an energetic release of the radioactive material inside the fuel. There are other reactor designs that can do that, and so molten salt's just one of those reactor designs. Thanks. Yeah.
Out of the pure curiosity, what are the technical issues that you're running into in regards to the digital twin software?
Well, there are lots.
You got a mic.
There's technical challenges with regard to how do you gather this data. The control room system is a 1995 computer. And so how do you get the data off? With the microphone. So there's elements of, how do you get this data out of this, this computer that wasn't made for this? How do you get it transported regularly, nightly, sent over to TAC in a secure way? There's obviously a whole lot with regard to that physics codes of how do we do the computing fast and efficiently, and how do we make sure it's accurate. And then as we get into more and more of the inference and calibration, there's going to be a lot with regard to the mathematics of what is it we need to calibrate, and how do we do that. In the real-time modeling, there is a whole lot. There are many different machine learning methods to try to do reduced order modeling, which are the right ones for which different problems, which different applications. And then on the actually using that real-time model, what is that user impact? What's the user interface look like? How does it change the way they operate the reactor and the experimentalists, how they use it? And then the autonomous control, there's physical components that need to be built and tested and evaluated, and understanding how we let the facility continue to operate the way it wants to operate without us messing up their operation. So throughout that whole circle, there are all kinds of research pieces connected to it.
I think with that, we will wrap up this one and move on to our next panel, which is focusing on medical applications of nuclear technology.